Hey kids, it's Miss Mooney. This video is about characteristics of function graphs and also about doing linear regression on the calculator. So we are going to be identifying different attributes of a function based on its graph, and the first thing we're going to start with is talking about positive and negative values. When I ask where is the function positive, I'm talking about where is the graph above the x-axis. So I'm talking about this part, and this part, and this part, okay? Those are the parts of the graph that are above the x-axis. So when I ask that, you're going to answer me with the x values that correspond to those y parts. This one would go on forever, and there's an arrow here, so this one would go on forever. So we would write that in interval notation. And we would say negative infinity to negative 2, because that's this part right here, soft bracket. And then we would also include negative 1 to positive 2, that part right here, with soft brackets. And we would include from 4 on to infinity. All soft brackets, because when we're talking about positive, 0 is not positive, so we don't include that one part where it touches the x-axis. And label that with positive, because those are the positive parts. So then the negative would be where it's below the x-axis. So if I highlight that, that's this part and this part. And so when we talk about the x's that go with those two parts, we're talking about from here to here, so from negative 2 to negative 1, and from here to here, so from 2 to 4. Next, we'll talk about increasing and decreasing intervals, and those are always read from left to right, just like you read a book, left to right, okay? So increasing would be the uphill intervals, so increasing would be this part, from the bottom of this valley to the top of this hill, and then again this part from the bottom of this valley on up. And there's an arrow there. So if we're going to write our increasing intervals, whoops, that's not what I meant to do. There, increasing, we would say from this value at negative 1.5 to this value, which looks like about 1/2 or 0.5. And from this value, which is a little bit more than 3, I don't know, we'll guess like 3.2, up to infinity. You would list both of them. When we're talking about decreasing intervals, I'll write smaller this time, that's where we're coming downhill. So that would be this part. Coming downhill from left to right, so from negative infinity to negative 1.5. And then also this part from the top here at about 1/2 to the bottom here at about, like we said, 3.2. So 0.5 to 3.2. Those would be the two decreasing intervals. All right, another attribute we talk about, local and then absolute maximums and minimums. So when we have a graph that has a bunch of turns, we have absolute maximums and absolute minimums, and we're talking about the tops and bottoms. In this particular one, if you notice, it's going up forever, so our absolute maximum is infinity. It does have an absolute minimum, a lowest y value, and that would be whatever that ordered pair is. Looks like about 3.2 and negative 3.5. But when we talk about local minimums and maximums, we're talking about when you are looking at just a specific area, bottoms of hills and tops of hills. Okay, so our local, we'll do it in blue, sure. Our local minimums are going to be at about negative 1.5 and, let's see, about, I don't know, negative 0.8. We will give you exact numbers on your test, so you won't have to guess. We also have a local minimum here. We said that was about 3.2, negative 4.5. And then we have a local maximum here at about 0.5 and about, I don't know, 3.2. Like that. Okay, another attribute, x-intercepts and zeros, which are the same thing as far as where they are on the graph. They're the parts where the graph crosses the x-axis. But what I want to specify is when you see the word x-intercept, then we write ordered pairs. So we would write -2, 0, and -1, 0, and 2, 0, and 4, 0. We would write them as ordered pairs. But if you're asked for just zeros, then you can write what x equals. You can say x equals -2, -1, 2, and 4. So the single numbers are called the zeros. The ordered pairs are the x-intercepts. All right, and then I also want to talk about the average rate of change. Rate of change, you guys know that just means slope. So if I'm just trying to find the slope between 2 points, if it's all curvy like this, I can pick any 2 points I want and find the slope. I just calculate using the slope formula. So you've got to make sure you know your slope formula, which is y2 minus y1 over x2 minus x1. So let's say I wanted to find the average rate of change from x equals 1 to x equals 2. So from the point right here to the point right here. Now it looks almost linear between those 2 points, but it's not. It's curved, but we can still just get those 2 ordered pairs. So we'll use the point at 1, 3. And the other point at 2, 0, and we'll plug them into the slope formula. So we would go y2 minus y1, we can do 0 minus 3 over x2 minus x1, so 2 minus 1 gives us -3 over 1. We have a slope of -3. The average rate of change from x equals 1 to x equals 2 is -3. Okay, now we're going to talk about modeling functions. We're going to learn how to use the HP prime calculator to create a scatter plot and calculate the line of best fit. And we can also look at statistical data on the calculator, and it can tell us how well that line actually fits the data that we have. So here we have a table that gives the average number of calories and total fat in grams of the food served in various fast food establishments. All right, and here's our fabulous HP Prime calculator. We are going to hit the Apps button, which is right here, okay? And we're going to choose the Statistics to Variable app. So you might want to write that in your notes so you don't forget it later. All right. And then the 3 buttons that we're going to use for all of this stuff are these 3 right here: the symbol, the plot, and the number. All right. We're going to first hit the NUM, the number. See, it's got a picture of a table. It might just bring you up there to begin with, but you're going to have what looks like a spreadsheet, and in column 1, we'll put the X values, and in column 2, you'll type in the Y values. And then when you want to look at your graph, your plot, you'll hit this plot button. And there's what your data looks like, all plotted on the screen. The screen is touch screen, so you can pinch it to zoom in and zoom out, and you can use the zoom feature on the on-screen menu also to zoom in and zoom out and get to where you can see all of your data points. So there's your scatter plot. To get the line of best fit, you're going to hit the symbol button, and then you'll have this screen right here. This right here where it says type, it's got a drop-down menu that you can touch on the touch screen, and you can change it to any type you want. The equation will show up right here. I have mine with 3 decimals because I did shift and then I hit the symbol button. It's got a little blue word that says setup, and I changed the setup to just show me 3 decimal places. Makes it a lot easier to read. A glitch that we have sometimes in our calculators is if we hit the symbol button, sometimes it only shows mx plus b. If you hit plot and then go back to symbol, boom, your numbers show up. I don't know why it's like that, but there you go. So that we have the equation for the line of best fit. Okay, now if you want to know how well does that line actually fit through the points, we can do a couple of things. If you go back to plot and you hit the menu that's on screen right here, well, let me get it color. There we go, on screen right here. It'll give you some more choices, and you can hit fit, and it will put a line. It will put the best fit line on the graph. So as you can see, our line goes pretty well through the dots, but there are outliers. There are dots that don't fit on this line perfectly. You know, if they were all exactly on the line, then we would say it was, you know, a really, really good line. So if we want to know exactly how good it is, we're going to go back to the number screen right here. Well, that's interesting. When I changed it to have 3 decimal places, it gave me 3 in everything, but that's okay. Doesn't matter. Go back to this screen, and we have this stats option right here. Just touch that, and you will see this. So what we're looking for is called the correlation coefficient, and that is a number between -1 and 1 that measures how well the line fits the data. And the correlation coefficient is little r. So on your calculator screen, that's this one right here, little r. And our little r is 0.847. So we've got this scale from -1 up to +1, with 0 being in the middle. If you get something close to 0, then it's not a good fit at all. The closer it gets to +1 or -1, the better the fit is. Positive just means positive slope. Negative means a negative slope. So we have a positive number. Our data points are increasing. We have a positive slope. And it's 0.847. So it's, you know, somewhere around right here. It's not perfect. It's not great, but it's still, I would say, pretty good. Pretty close to being a good fit line. And so finally, we can use all this information, the scatter plot, the best fit line, the equation, to answer some questions about this situation. So I'm going to put some up on the screen and we'll answer them. First question, what is the slope and what does it represent? So we already found the equation. Remember, it was y equals 0.046x plus 1.179. And if you remember y equals mx plus b, the slope is going to be the 0.046. Now, what does this represent? If you look, slope is always rise over run, and our rise is the fat, and the run is the calories. Okay, so when we reduce the fraction, we're going to end up getting 0.046 fat grams, or fat, we'll just put fat, per calorie. Okay, so that's 0.046 grams of fat for each calorie. All right, next question. What is the y-intercept and what does it represent? So I erased the equation, but our y-intercept was the 1.179. 1.179. And what does it represent? Well, if you look on the graph right here, the y-axis is fat, the x-axis is calories, the y-intercept is when calories are 0, so that would represent the fat in a food. Sorry about that. Food with 0 calories. I don't know if that's true or not, but that's what it represents in our situation here. Next question. If a food has 300 calories, how much fat can you assume it has? So I'm giving you an x value of 300. I'm just going to take that equation I've got and plug it in. Y equals 0.046 times x, so times 300, plus 1.179 gives us about 14.979 grams of fat. We'll just go with 3 decimal places because that's our default. And is this an interpolation or an extrapolation? Remember, interpolation is if it's within the domain. So basically, if we're plugging something in between here and here. And 300 is between here and here because our lowest x value was like 130 and our highest was about 500. So it's, somewhere over in here, I guess. Interpolation, that's the important thing because it's within the domain. If it was outside of the domain, it'd be an extrapolation. And my last question that I present to you, if a food has 25 grams of fat, what can you assume is the calorie count? So this time I'm giving you the y value, which means you take the equation, plug it in for the y value. 25 equals 0.046x plus 1.179. Subtract, divide, and you should get an x of 517.848 calories. And that is the end of our video. So you guys have a great night.